Hi everyone, welcome and thank you for coming to our Spring into STEM virtual lecture on smart manufacturing in the digital era. The session is going to be led by my colleagues Max and Reza, and my name is Kate Wilson. I'm an Outreach and Communications Officer in the department. First things first, this session is going to be recorded. It will be available on the Faculty of Engineering website in due course. The session will first consist of about half an hour of presentation and then half an hour of questions and answers. So if you do have any questions throughout the whole session, please feel free to pop them in the Q&A box, which you can find at the bottom of your screens, as Max and Reza will be more than happy to answer them. So without further ado, let's get started. I'll hand over to Max.
Perfect. Good morning, everyone, or good morning. It's after 12 p.m., so I don't think we can say this anymore. It's a nice sunny day, at least that's what I wanted to say 5 minutes ago. Now it's raining, but still a wonderful time to talk about science. And I hope you can see my screen. Good. So today we're going to talk about smart manufacturing in the digital area. And we is myself and Reza Abbasi, and the two of us are lecturers in digital manufacturing of advanced materials in UCL's Department of Chemical Engineering. So I guess we don't have to look far. We want to look for challenges, and challenges that make us need new ways how to manufacture goods. Very recently, we all experienced the pandemic, and we saw how important it is not only to develop a product, in this case, to develop a vaccine, but also to find ways to manufacture it, to find ways to develop processes, large-scale processes very rapidly, and how important this is. We also have a climate crisis. We also have rising costs of living and, of course, energy. So we are facing quite a few challenges. And looking back, what always helped us in the history to tackle challenges are new technologies. And this, we hope we can contribute to this as well. So using the words of much smarter people, the great growling engine of change, technology, or a saying I very much like that reminds us not to be afraid of new technologies, but to make sure we are part of it, is once a new technology rolls over you, if you're not part of the steamroller, you're part of the road. So I mentioned history, so let's look back in time again. So how did new technologies change the way we live, change the way we live and work together as a society? So very dominant, very obvious is that the first industrial revolution, and that was end of the 17th century, where new inventions such as the steam engine, and with this new ways to transport goods and people, and also new ways how we manufacture textiles, help not only the textile production, also mining, metal processing, agriculture, of course, transport, and massively changed the way we manufacture goods and therefore also the way we live and the way we work. So that was the end of the 17th century. And it took some time, but again, it was a leap in technology. In this case, it was things like the invention of the telegraph. You remember, we were able to start as a humanity, start communicating over long distances. The first telegraph message was sent in 1844. We established railroads, so we were able to transport, if you want, could be considered as the onset of globalization. And very important, we established electricity, not only in our households, also on manufacturing side. And that helped massively by modernizing production lines, as well as gas, water supplies, sewage systems. I mentioned communication before, and again, that helped us to facilitate faster transport of goods, people, and ideas. Well, it took some time, and depending on how old you are, I definitely was part of it. You might have been part as well of the third industrial revolution. And again, it was a leap in technology that made this possible, a leap in manufacturing, to be precise again. What was it this time? Well, it was the way we were able to manufacture semiconductors or integrated circuits, or you might know them as computer chips. So we were able to make them much smaller, much more powerful, and that helped us within a few decades to come from little radios to computers. And just to remind yourself what you have in your pockets, your smartphones, semi-smartphones, however you want to consider them, they are much more powerful in terms of computers than what was used to fly to the moon the first time. So again, end of the 20th century is when computers not only made it into our households, they also made it into manufacturing sites and massively changed the way we work. And as well, very important, robots made their way into manufacturing sites. So that was the third one. And the question is now, there are new technologies coming up. Are we in a fourth industrial revolution, kind of extending the third industrial revolution I just spoke about? Well, what is Industry 4.0 or the fourth industrial revolution? It's a term first used about 10 years ago. And what are the new technologies that we think are sparking such a new revolution? Well, these are the rapidly growing fields such as robotics, artificial intelligence, nanotechnology, quantum computing, and of course, the leaps we have in biotechnology, gene editing. I spoke about the vaccine, the pandemic before. So you see, we have new ways also for therapeutics and vaccines. We're talking about autonomous transportation and many more. When we're speaking about the fourth industrial revolution for manufacturing, what we have in mind are things like a smart, intelligent, or a smart factory. What is that? That is a production environment that without human intervention is able to produce and manufacture. So machines and operations are connected, linked to each other, communicate to each other, and operate autonomously in a way that humans are not needed anymore to actually do the tasks. We're speaking about things such as predictive maintenance, where machines and operations or manufacturing lines have multiple sensors integrated that communicate with each other and identify before things are not working properly, if something is malfunction, if something is out of the ordinary. So that helps us to predict failure before it even happens, and much more. You might be familiar also with how rapidly additive manufacturing technologies such as 3D printing have developed over the last 10 years. We can not only print plastics, we can print metals, ceramics, composite materials, and that massively speeds up prototyping and therefore, of course, reduces the time we need to develop a process. So speaking about manufacturing and smart manufacturing in the digital era or within the fourth industrial revolution, so we will speak a bit about how we manufacture goods and how smart manufacturing is helping us to develop processes. And that is done by Reza, so I'll hand over to him in a few seconds. And we will also talk about how we develop new advanced materials, why we need them for, and how computers and the digital era can help us to develop new materials. Good. This is where I hand over to Reza.
Thank you, Max. Hello, everyone. I'm very happy to be here with you today. I'm going to talk a bit about computers and their applications in this digital era and how they can help us to develop processes. If we can go to the next slide, Max. Well, computers as fancy calculators basically are helping us to do lots and lots of calculations to solve numerous equations in a very short period of time. We use them for very different tasks, such as process modeling, which is I will discuss a bit in more detail later on. To predict the system behavior, we use them to look at the data, to analyze the data, discover patterns, to interpret this data, find interesting facts about the system. Also to optimize these processes, to maximize or minimize a given objective variable, while we abide by some constraints, for example, to maximize our profit without violating our product purity. Another application can be how to see how a process is affecting the environment, which is done through life cycle analysis. These activities plus a lot more are part of our tools that we have for digital design, digital manufacturing, and process automation as a very important part of all of this. So talking about process modeling, first of all, we mainly have two approaches to process modeling. We can either use laws of physics, which we as a result, we call them physics-based models or mechanistic models. or it can come from data. So without knowing what's really going on in the system, we just look at the input-output data. We try to use data-driven methods in order to find relationship between these data in order to describe the system. This is Max will discuss this a bit more in detail, but talking about mechanistic models, this is an example where here we can see a fluidized bed reactor, which is used to produce polyethylene. The feed is fed into the reactor from the bottom. We have ethylene, butane, hydrogen, nitrogen in a gas phase. The catalysts are lying as a bed inside this reactor. So the gas fluidizes this solid catalysts. The reaction happens. The product forms around this catalyst and then leaves from the bottom of the product. And after some processing, we would get something like that. The unreacted gas leaves from the top, and again, after some extra processing, it's recycled back to the reactor, and this process goes on and on. So as you can see, it's fairly complicated process. We have very different phenomena going on here. We have the complex kinetics of polymerization, which has many different steps, which should be described in a mathematical form. We have the mass and energy balances that should follow the laws of physics, the conservation of mass, energy, and momentum. We have the hydrodynamics. We have the physical properties of the system. Each of these components have their own properties, and their combination, when they mix together, can lead to a fluid that has different, for example, physical properties. So in total, we have lots and lots of differential equations and algebraic equations, which needs to be solved together. When we solve all of these together, we have our model, but we still are not sure that if this model is valid. So we need to go through the validation process. To do that, we look at the real data. This real data can come from a lab scale process, a pilot scale, or industrial scale. We compare how our model prediction match those of the real world experiments. If it's not valid enough, we need to fine-tune the models. For example, each of these models have their own parameters that can be fine-tuned in order to improve the model prediction capabilities, which Max would also touch upon later on. But this is the downside with this approach is that these models are offline. They are not connected to the real world process. Hence, we have this digital twin nowadays. It's a new concept, but use the old technologies. So the computers, the powerful computers nowadays allow us to have digital twins, which is visualized here. That basically represents a potential or actual physical asset, process, or system. The difference between this approach, this digital twin, and the model that I explained earlier on is that these are interconnected. There is live two-way real-time data transmission going on. So we use the live data from the physical plant in order to improve our model. We also use the live prediction capabilities of our model in order to control the physical system. In bottom right-hand side, you can see the physical twin has different kinds of data. This data can come from sensors, from process conditions, from other types of data, such as weather conditions or feed, for example, specifications. These would all come to the data management system. Then it's fed to the models that we have. We can have one of these kind of models, mechanistic or data-driven, or we can have both to have the best of the both worlds. And then we can use this model to optimize or control the system. These digital twins have very different applications throughout the life of a process. We can use them in the very first step of design to simulate in order to scale up the process, to estimate the costing in order to come up with the best design that we can. During the operation, we can use these digital twins for soft sensing. So, for example, to estimate parameters, the variables that are hard to measure or impossible to measure. Can use them to minimize or minimize the emissions, to control and automate the process. Also during the decommissioning step, in order to schedule the process and the costing involved, and also to abide by the safety regulations. To give you an example of how this would work, here is an example from the literature. This is a fermentation process. These applications can be in very different fields. In this case, it's a fermentation process. So the authors have used the data-driven methods in order to estimate the current concentration, current state of the glucose from spectroscopic data. So we have live data coming from the analyzers to the data-driven model, and the data-driven model can estimate the state of the glucose. We also have mechanistic models, the kinetics, in order to estimate the concentrations. And these combinations basically allows us to understand the system in more detail. We can use it to monitor the system, also forecast the future. What would happen if we change, for example, the concentration or anything within the system? Another example, which is an interesting example as well, this one is in a pilot scale. So it's not a lab scale. In this case, it's a pilot scale plant. This is a continuous wet granulation and tableting process, a process fairly common in pharma industry. In this case, authors have basically developed their digital twin. The advanced process control platform in this case is the backbone of their digital twin. So everything is fed there. So we have the mechanistic models that is feeding information to the advanced process control platform in order to, because we have model predictive controller. So based on the model predictions, we can control the system. We have the IoT platform, which sends the data to the cloud in order to visualize, for example, the process. And this process control system is also controlling the physical process itself at once. So we talked about digital twins. We also talked about physical models, but there are a lot to be done we can do to improve the models, which is something that Max will touch upon in the next session, in the next part. Over to you, Max.
Perfect. Thanks a lot, Reza. So Reza just showed nicely what we can do if we have a model, what a digital twin can do, how we can develop processes and monitor processes on computers. But it's a luxury when we have a model, because there are many cases where we do not have a model, or what can we do in these cases? So let's consider a very simple chemical reaction model. Let's assume methane reacts with oxygen, and that gives us CO2 or H2O, or no need to talk about chemistry today. We can just say A plus B gives us C and D. And we would like to have a model for this process. Well, we could pick our brains. We understand physics and chemistry, and we know a few things. We know that the more A we have, the more faster the reaction happens. We know that if you have a higher concentration of B, then the reaction will happen faster. But do we know exactly how the concentrations of A and B affect the reaction rate? Not really, but that's a pity because we would like to know the reaction rate. The reaction rate is what tells us how fast the reaction is happening and how long we would need to run the process. Is it seconds, minutes, days, weeks? Because that obviously determines very much how we develop a process and how we can develop a process that does the thing in the most efficient and sustainable way. So I skipped a few steps and you have to trust me on this. So what you see here on the bottom right is an equation for the reaction rate. And this is what I mentioned before. We do know the physics a little bit, so we're able to come up with equations like this. And they contain things like PA and PB, which are the partial pressures. We're talking about gas here. That's why you see partial pressure and not the concentrations in things like mole per liter, what you might be used to. So PA and PB, again, tells us the concentration of the components A and B. What is also in this equation on the right side here are 3 model parameters. So we have parameters in our model, and here is where it gets problematic. We do not know the values. So what is usually done in this case? We have a model, but we're not fully there because we don't know the values of these parameters. Well, the standard approach is, okay, we have a model, we need parameters to be estimated. Let's do some experiments. So we do some experiments and then we ask our computers, okay, we have now experimental results. So which parameters in this model equation I just showed would have had the highest likelihood to yield the experimental results we just had a look at? Okay, then we have a first estimation of the model parameters, the K1, K2, and K3, and we repeat. We do new experiments at new settings, for example, new concentrations of A and B, and we see most likely that the model doesn't really match. So the new experiments are a bit in disagreement with the model, which means we're not yet there. So we have to do the thing again and the circle closes. That's very labor intensive, and I like to refer to this as the work of Sisyphus. If that doesn't mean much to you, have a look in Greek mythology and what the punishment of Sisyphus was, the endless task he was punished with. So that's why I made this analogy. Well, can we do something better? How can smart manufacturing help us in this case? Well, the best thing is if machines do the work for us and not ourselves. And that is an example shown here. So this is a flow chemistry approach to do this and to automate the estimation of parameters in a model. So what is flow chemistry? You don't really put something in, if you want, in a BK reactor and you get it out. You have continuous flowing systems. So what you see here on the left case, on the left side is you should see my cursor now. It's methane and oxygen. Nitrogen is a carrier gas, is inert, is not participating in this reaction. And these 3 gases, their flow rates, or if you want, that's equivalent to the concentrations then, are mixed or controlled by the mass flow controllers, by the MFC. They are mixed, and after the gases are mixed, they're entering a microreactor. So we're using very small reactors, making sure that the reactor volume is small and we're not wasting a lot of material because, of course, consumables are precious and we don't want to use and waste a lot on these by doing these experiments to estimate the model parameters. Okay, so we have the gases at the concentrations we want because we set the flow rates entering the microreactor. In this microreactor, we have a catalyst embedded. The catalyst is doing the trick. So the catalyst makes sure the reaction is happening and hopefully the way we want. And once they exit the microreactor, the gases are analyzed in the GC, which is short for gas chromatography. So we know the concentrations of A and B because the mass flow controller is determining it. And we know, thanks to the GC, the concentrations of C and D that comes out. Okay, so we have a way to do this experiment, but even better, we fully automate this, meaning that there is a brain behind there. So we have smart algorithms that learn and suggest new experiments that gives us the maximum information, i.e. suggest the experiments which tell us most about these parameters. So the way it works, if you want, we run a small set. You might hear the expression design of experiments. Let's say we run 10 different concentrations of A and B. We have this, we have a first estimate of our model. And then autonomously, the system itself will keep on continuing, suggesting new experiments and on the way improving the accuracy of the estimated parameters. So that's the procedure here described in a nutshell. So we start with the initial set of experiments. We then train the model and let the computer decide which experiments to do best. And here comes the best bit. This is done autonomously. So the computer does this, learns, suggests new experiments, and only stops once satisfied. So without any human interaction. And that actually is work done by Solomon Baba, who is also on the call. So if you have any questions related to this, he can certainly help you out. I have to admit, I was lying to you. I was speaking about 3 parameters before. Actually, there were 6. So what you see here, 10 experiments were performed to get the model to an initial idea, to have an initial idea of the estimations. And then more and more experiments were performed by the automated system without any operator clicking any buttons. And with every experiment, we learned more about the parameters. We learned more about the accuracy, which is why you see the error bars as well getting smaller and smaller with each experiment. And after 22 runs, we were rather confident, okay, we are now sure we have the model parameters. Therefore, we have a nicely calibrated model, which can then be used in the digital twin to develop or optimize processes. So far, so good. That was a bit of how smart manufacturing helps us in terms of process development. But we also need new materials. Let me quickly remind you of the challenges we talked before. So we have new demands on the way we generate and store energy. Of course, we have new demands for healthcare and medicine, and new demands for sustainable process development and manufacturing. So we need new advanced materials that improve the technology we have at the moment. If I say advanced materials, it's if you want the best word, but let me give you some examples what I mean by this. I mean things like drug molecules and pharmaceutical, porous materials for energy generation and storage. I mean catalysts facilitating sustainable processes. I mean functional nanomaterials for precious metal recovery, nanomaterials for biomedical applications, and many more. So these are kind of materials I speak about when I speak about advanced materials. So let me give you one example of our research, and that is magnetic nanoparticles for hyperthermia cancer treatment. Well, what's the idea here? The idea here is that we accumulate magnetic nanoparticles in tumor tissue, and we then expose the patient to an alternating magnetic field, which is nice because magnetic fields do penetrate the body. Unlike light, if you shine a red laser or typical lasers on your skin, they work very superficial. Magnetic fields, however, can penetrate through the body. So it is a way, even if you have a tumor in your brain or deeper in your body, hyperthermia should be an option. So again, what is happening once we have the patient with a tumor and the magnetic nanoparticles accumulated in this tumor in an alternating magnetic field, if we have the right particles, the particles will start generating heat, and the generated heat is affecting cancerous cells more than healthy cells. So tumor tissue, cancer cells usually have a lower heat resistance and die quicker when we temporarily increase the temperature. So that is the idea of hyperthermia cancer treatment. It's not yet on the market. The first clinical studies on this technology have actually started last year. However, it's researched since many decades. And why is it so complicated? Why does it take so long to bring such an idea to the patients? Well, material development is very much a bottleneck for this. We need our magnetic nanoparticles to be non-toxic. They need to have the right size. They need to have the right surface chemistry. They need to emit heat when exposed to an alternating magnetic field, and more. It's a long list, and usually you can optimize for 1, for 2, but to get all the criteria right, it is a very, very difficult task. Why is it so difficult? What is the challenge? So let me use another example to highlight why making complex materials is very difficult. So thinking back of our simple example, that was a reaction A plus B gives C and D. And with a bit of thinking, a bit of prior knowledge, we were able to put a model to it. That's fantastic. However, when we're talking about these advanced materials, we do not have that luxury. And why is that? Because in many times we don't even know how exactly they are formed. We just know that they're formed through multiple steps. So A plus B gives C and D, might give us E and F, G and H, and maybe a few steps later, we get the product we're after. And each step is very sensitive to the process or synthetic conditions. So we don't always know how this many synthesis parameters actually affect what we produce. You could say, well, that's not a problem. We just do a lot of experiments, and you're not wrong with this, but there's a caveat to it. So let me give you this example. We would like to produce nanoparticles, and we're interested in, okay, what has the highest yield? So the amount of specific product formed per mole of reactant, if you want the definition of the yield. So we're interested at what temperature do we get the highest yield? Well, we could set a range and say we do 50 experiments and we will find the temperature that gives us the highest yield. So said, so done, we do the 50 experiments, we do that. That was easy. What if you also want to consider pressure? Pressure also has an effect on how these particles form. You could say, okay, let's do the same exercise again. We do 50 experiments at each pressure and each temperature. But now you see where I'm going with this. We already have 2,500 experiments in this case. And it will not surprise you when we're talking about these advanced materials. We're not talking about 2 or 1 synthetic variables. There are many things that affect the synthesis. And very likely you enter with 3, 4, 5, or even 6 synthesis variables. And if you want then to screen the synthetic variable space, the way I mentioned before, we end up with millions, billions, and trillions of experiments. So to say it mildly, if we choose this purely experimental approach, we are in trouble. Or to use another analogy, we're looking for the needle in the haystack. Just in this case, we're not even sure we'll find a needle because there's no guarantee we actually find the material we're after. So we need a savior. So what can save us? Well, high throughput experimentation for material discovery is one of those saviors, one of those tools that help us to do not 1, 2, hundreds, but even thousands of experiments in one day. We could talk hours and hours about this, but let me just give you a few buzzwords. We already mentioned flow chemistry. There are robotics that are more and more integrated in labs. If you go in a biolab, since decades, you see massive liquid handling robots. We have more and more advanced analyzers that can measure concentrations of sample, for example, overnight, and we have hundreds and thousands of samples, and they can do this. And it's a nice integration of software, robotics, and new technologies that help us to do more and more experiments in the lab, also at smaller scale, so not to waste too much material on the look for these parameters or best materials. Well, let me give you one example. We talked about flow chemistry again from our research. And this is how we actually synthesize these magnetic nanoparticles for hypothermia cancer treatment. So without going into details how this synthesis is working, we had an idea how to form the particles and which reagents will give us the size and shape we want. We had an idea, we didn't know exactly what to go for, and we used a flow chemistry setup. So not sure if you see this on the resolution. So we use segmented flow, means we disperse an aqueous phase in an oil phase. So we have these little droplets here in blue, and each droplet, if you want, is a closed system. So every droplet is a little reactor on its own. Or a video says more than 1,000 words. So this is obviously a blue dye and not the magnetic particles. But that kind of gives the concept away. So again, what you see here in the outlet are these nice blue segmented elements, and every element of them is one reactor and therefore could be a single experiment. So that helped us then to make nanoparticles which are of the size we wanted and also colloidally stable, meaning they do not agglomerate and stay nicely stable in solution. So that now here, not sure if you see my cursor, but these are solutions of magnetic nanoparticles. And the flow chemistry tool actually also helped us to find the conditions in our setup that make them the way that they heat nicely when exposed to an alternating magnetic field, which is a key attribute for the magnetic magnetically induced hypothermia cancer treatment. Good. We talked about experimental techniques a little bit. So keeping in mind the problem, that still doesn't help us. So I guess you got the idea that with robotics, flow chemistry, and all these tools, we can go to hundreds and thousands of experiments per day in theory. The devil's always in the detail, but still, even that is not helping us on the purely experimental approach. Because remember, if you have 4, 5, or 6 synthesis variables, which is absolute the standard, we end up with millions, billions, and trillions of experiments. So even if we do thousands of experiments, we're not there, not even the right order of magnitude. Well, and this is where digital manufacturing again should help us. Of course, we can pick our own brains, but we will reach limitations soon. And that's where we ask for computers to understand how these multi-dimensional variable spaces are interconnected. So we are asking for the help of machine learning and other digital tools now to help us navigating efficiently through this design space. And why is that important? Why is it important for us to understand how these synthetic variables are correlated? Well, think again of that design space we have to screen and navigate through. If we understand how certain variables relate or correlate to each other, we don't need to screen the entire variable space. We don't need to screen and do experiments in every element of this multidimensional space. If we understand the dependency of synthetic variables, how they affect the product we're after, then we don't need to do that many experiments. So that is one way then to navigate through this hyperspace. So what do I mean by this? Let me start with a very simple example. Let's speak about nanoparticles again. We have a nanoparticle size. We do some experiments at a different temperature, and we realize there's a linear dependency. So at higher temperatures, we get smaller particles. At lower temperatures, we get larger particles. So it's nicely done. We do 10 experiments, and we understand there is maybe something like a linear relationship. And if we're after high temperature, after large particles, we know now, okay, we have to operate at lower temperatures. And that helps us already guiding through the multidimensional variable space. As nice as these linear models are, however, as useless are they, because the things are usually much more complicated. What could happen here? We're not interested only in the size, also the yield. Again, we have not considered pressure and concentration. So linear model most likely is not sufficient to understand how these variables correlate. And this is where we can rely, or we can ask for help from tools such as machine learning. So what you see here on the right side is a graphical representation of an artificial neural network. So it's drawn here the same way I could write out an equation. So what you see here with all these dots and lines, you could put in not actually a very complex equation, but it will be a very long one. And why is that? So every dot and every line here in this model. So again, let me explain the inputs and outputs first. So what this model does, it relates outputs such as particle size, yield, if you want color, shape, all these things on the right side, to input variables such as temperature, pressure, concentration, pH value, viscosity, mixing conditions, whatnot. And the neural network is that model that correlates these inputs to the outputs. Well, I spoke about that every line and dot is a parameter. That means we do need quite a few of experiments to get them. So if you have hundreds of parameters, and that neural network has several hundreds, we need thousands of data points that help us to understand, to calibrate this model. Because remember what we talked about before with a very simple chemical reaction model, it's not different from these models here. So what these models, such as the artificial neural network does, it allows us to compromise much more complex relationships into a model. But again, thousands of experiments, this is something we can do. This is where robotics and flow chemistry and these technologies help us. So that is how the combination of machine learning and these high throughput experimentation techniques can give us what we want. And things like this neural network could be a way that tells us how to navigate through the parameter space, meaning we don't have to do these billions and trillions of experiments. Well, these neural networks are beautiful, and if you want, also dangerous, and we also refer to them as data-driven processes. Reza mentioned it as well in his part, or we also call them black boxes, because as beautiful as they are, and that holds true not only for neural networks, for many machine learning techniques, as beautiful as they are, we don't really know how this knowledge is embedded. It's very hard to interpret this equation. Remember the equation we had before for the chemical system? If I would write down the equation for the neural network, it would be so long. At least I would certainly not be able to understand how the input and outputs are related. So that is also one reason why we call this a black box. But to repeat myself, this black box model, although we don't fully understand it maybe, it can help us now to navigate through the parameter space. And since we're not asking for trillions of experiments, we're asking now maybe for thousands of experiments to calibrate this. That is something where you might not like someone in the lab asking for thousands of experiments, but with the help of robots and other technologies, we can now deliver this, and machine learning and high throughput experimentation integrate nicely together to develop new materials. So if topics like this interest you, and you might ask yourself, where can we learn more about digital manufacturing? Well, Reza and I have a new workplace, and that is the Marshgate building in UCL's new campus, UCL East. And within the Marshgate building are the manufacturing futures labs. And these labs focus very much on all the topics we discussed today, and very much on robotics, continuous processing, automation, and of course with other research focuses in the Department of Chemical Engineering, such as machine learning and autonomous processing. So these manufacturing futures labs, they will be filled with life and also teaching programs. Those are the digital manufacturing of advanced materials, where Reza and I are lecturers. There's also the nature-inspired solutions program, and our neighbors in the advanced propulsion lab have another new MSc, that is the advanced propulsion program. Speaking about digital manufacturing, of course, I'm very privileged to be the program director of this, and glad to do this together with Reza. If you're interested in digital manufacturing, have a look further on our program website, on the Chemical Engineering department, as well as our YouTube videos, or feel free to reach out directly if you have any questions in this field.